In this video, I want to talk about quantifiers, logical quantifiers. But first, we need to talk about definition. An open sentence or predicate is a sentence with one or more variables in it. And it becomes a proposition only when the variables are replaced with particular objects. So for an example, I might say P of X, and the statement will be X equals 2. Or I might have the statement X squared plus Y is greater than 2, and that is an open sentence with two variables, so I'll say P of XY. The true set of a predicate would be the set of objects in the universe that make it true. And two predicates are equivalent if they have the same truth set. And the truth set's going to depend on the universe. For example, let's say I have two predicates. P of X is X to the fourth equals 1, and Q of X is X squared equals 1. If my universe is the natural numbers, then the truth set for P of X and Q of X is both 1, the number 1. If I'm talking about the integers, then the truth set for both of them is plus or minus 1. Same thing for the reals or the rationals. That doesn't change. Now, what gets interesting, though, is if we have complex numbers. If you've got complex numbers, then the truth set for P, you're also going to get I and negative I. So it's bigger. So whether it's true or not depends on your universe. The first quantifier I want to look at is the universal quantifier for all. For an example, I might say for all X, X squared plus 1 is greater than 0. I didn't talk about the universe. Typically, we would assume real numbers unless otherwise stated. We also tend to use the variable X for real numbers, whereas N we might use for integers, or I as positive integers or counting numbers. So this upside down A means for all. The next quantifier is the existential quantifier. Makes me think like we're studying Hume or something, David Hume. Existential means there exists. Oh, that should have quotes at the end. Oops. For example, there exists an X such that X squared equals 2. There's actually two numbers if we're assuming the reals, square root of 2 and negative square root of 2, but to say exists just means there's at least one. And that's the backwards E for exists. See, it kind of works out there. Now, what if we want something unique? We want to say there's exactly one. There is one and only one. Well, then we put an exclamation point after it. Oh, my head's in the way. I'm going the wrong direction. So if there's a unique one, we use an exclamation point. We say there is a unique X such that X squared equals 0. And that's the symbol for that. So assume that our universe is the real numbers. Which of these statements are true? Which ones are false? Well, let's see, I've got for all X, X plus 2 is greater than X. Well, yeah, we subtract X from both sides. We get 2 is greater than 0. That's correct. That's true. For all X, X is less than or equal to 3. Well, if we're in the real numbers, that's false because 5 is not less than 3. So that one's false. For all X, the absolute value of X is greater than 0. And that is clearly false. Sometimes there's just one that's going to screw you up. If X equals 0, that statement's not true. So the whole statement is false. Let's look at some of these existential ones. There exists an X such that X squared is equal to negative 1. Well, our universe is the real numbers, so that's not true. No square is equal to a negative number in the real numbers. You have to start getting into the complex imaginary numbers. So that one's false. There exists an X such that X squared minus 2 is equal to 5. Is that true? Well, sure. We've got X squared is equal to 3, so X is equal to square root of 3. Sure, that works. There's a unique X such that X squared minus 2 is equal to 5. Now, this one's false because we actually have two of them. We've got the square root of 5 and negative the square root of 5. So this statement is false. Theorem. If I want to negate a for all, it becomes an exists. A negation of the statement. Now let's say this in English. So if I say everyone in the class is under 30, well, that's clearly false. And I only need one person to screw it up, and that's me, because I know you can't believe this, but I'm actually not under 30, I'm over 30. So this statement would be false. So the way to negate a for all is there exists. There exists one thing that screws up the statement. Similarly, if you want to screw up or negate if there exists, There exists someone in this room or in our class that's 100 years old. Don't go there. There exists someone in our class that's 100 years old. Well, that's not true. That means for everybody in our class, nobody is under, it's not true that they are under, they're 100 years old. I'm getting tongue-tied. So let's look at this example. Suppose I have this statement, no right triangle is isosceles, and my universe is all right triangles. How might I write that in a mathy way? Well, my universe is all right triangles, which is kind of weird. I don't usually like universes that are that specific, but okay, our universe is all right numbers, right triangles, and no triangle is isosceles. So I might say, it's not in some of the books, but it's easier to say there does not exist. So there's no T in the universe where T is isosceles. Or you could say for all T in the universe, T is not isosceles. Both of those are fine. Oh, by the way, the statement is false, obviously, because you can have an isosceles right triangle, easy peasy. That's a 45-45. There is a smallest positive integer. How would we write this? Well, there is translates to there exists. Smallest positive integer. So I know that it has to be a positive integer. That's the symbol for positive integer, funky Z with a plus. Now, how do I say, I don't want to just write the sentence because that defeats the purpose of changing it all into mathy talk. There exists an X that is the smallest positive integer, which means it's less than any other integer. It's less than for all the other integers, or equal to, because we don't want to leave out the X. So then I will say for all Y in the positive integers, X must be less than or equal to Y. Now, the reason I say are equal to is you need to include the possibility, since I said for all Y, that would include X because X is in there also. It's kind of a technical thing. Clearly, this is true because X equals 1 when X equals 1. For every positive number X, there exists a Y such that X squared plus Y equals 7. Okay, so this one's is a little laid out a little bit nicer. For every positive number X, so they didn't say what kind of number, but since it's positive, it can't be complex. So we're going to assume it's a real number. So for all X in the real positive reals, there exists a Y. They don't tell us anything about the Y, so we'll just assume it's in the real numbers, or we just won't say anything. There exists a Y where X squared plus Y equals 7. And this is true because you just let Y equals 7 minus X squared. So, sorry, it's not flipped around. So any X squared you choose, my Y will be 7 minus X squared. That's kind of the key. When the first one is for all, that means I can grab any of this set and you have to find one that exists that makes the statement true. Order matters. Going along that same line with you choose and I choose, or you cut and I pick. Consider the statement, for all X, there exists a Y such that X is equal to Y squared. Assume we're in the positive real numbers. Versus there exists an X such that for all Y, X equals Y squared. Now let's look at this first statement over there. This means take any X and I can find a Y such that X equals Y squared. Well, since we're in the positive real numbers, I can do that. If you grab an X and throw it to me, I'll just choose Y to be the square root of that. So this is true. Now look at the other side. Here it says, there is an X out there such that no matter what Y I come up with, that X will be equal to Y squared. If I choose Y equals 5, then X equals 25, because I can choose any Y I want because it says for all. So if I have Y equals 5, then X equals 25. If I have Y equals 3, then X equals 9, because X equals Y squared. So therefore, 25 equals 9. Yeah, no, that's not true. So this statement is false. Order matters. Let me leave you with one more example and let you contemplate the difference between there exists for all and for all there exists. Suppose P of xy is the predicate that X hooks up with Y. What is the difference between for all X, there exists Y, P of xy, versus there exists X, such that for all Y, P of xy? What is the difference between these two statements? And I'll leave that with you to think about. And that's a good place to stop.